Now that we've learned about energy level diagrams and electron configurations, we can see how the periodic table can help us fill out electron configurations more easily. So this diagram here obviously shows you the periodic table, and it has the elements color-coded by what we call blocks. And so we call all these purple ones right here the S block elements. So these ones right here are called the S block elements. And that's because when we do their electron configurations, the final electron will fall in the S orbital. These ones over here to the right are called the P block elements right here. And again, that's because the final electron is going to be placed in the P subshell. The ones in the middle are called the D block elements. Same reason. And the lanthanides and actinides are called the F block elements. Again, same reason as before, their final electron will land in the F subshell. Note here that helium is actually part of the S block elements, and that's because if you look at helium, helium's electron configuration, so helium has 2 protons, right? And its final electron, 1s1, 1s2, its final electron still falls within the S subshell. So again, probably the best way to do this is to look at some examples. Okay. One thing I should note here is that these F blocks right here, they come after the 6s subshell. So please note over here, we're going to put little stars, that once you finish with 6s, you jump down to 4f. And there's a little bit of an anomaly. It actually fills up the D subshell with 1 electron and then it jumps down. Okay. But we can see this using the energy level diagram that we saw previously. So I'll show that right there. Just remember that after 6s, you go to 4f, then you go to 5d. Let's see if that's reflected in our energy level diagram. Okay, returning to our energy level diagram, you can see that 6s is here, then 4f is the next highest in energy, then 5d, then back to 6p. So let's go back to our periodic table. And we see that reflected here. 6s, fill up 4f, then fill up 5d, then go to 6p. Valence shell behavior. Recall that valence electrons control the chemical properties of an element. Therefore, only the outermost electrons, the highest principal quantum number, control the properties. So the important thing to remember here again is that valence electrons are the electrons with the highest principal quantum number. And that's given by the variable n. The inner core electrons, those that replicate the preceding noble gas, do not contribute to the chemical properties of an element. So chemical families share similar outer electron configurations. So we're going to use this periodic table here to do the electron configurations for lithium, sodium, and potassium. So if we look at our periodic table, lithium falls right here. This is the lithium element right here. And so I can use this periodic table and your periodic table to find out what lithium's electron configuration is. So if lithium is here, I'm going to say 1s1, 1s2, 2s1. Okay, so let's write that out. Lithium, which is 3, 1s2, 2s1. Again, I arrive at that by saying, okay, I've got to fill up the 1s subshell here, so 1s1, 1s2, so I'm at 1s2. To get to lithium, I have to go 2s1. 1s2, 2s1. I look at sodium. Sodium is given as, has the atomic number of 11, and sodium is right below lithium, right here. So if I take a look, I go 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 6, 2p6, 3s1. So just to repeat, in order to get to sodium, I go 1s2, 2s2, 2p6, 3s1. So that's how you can use your own periodic table to figure out these electron configurations without having to go through drawing an energy level diagram. Similarly, if I look at potassium, potassium's right below it. And we'll do this one a little bit quicker. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Okay, the next thing it asks us to do is circle the valence electrons. Recall, valence electrons are the ones with the highest principal quantum number. So I'm going to circle this right here. Highest principal quantum number, 1 valence electron. Highest principal quantum number, 1 valence electron. Highest principal quantum number, 1 valence electron. And so lithium, sodium, potassium are all part of the alkali metals. They all have 1 valence electron, which makes them chemically very similar. They're all highly reactive. They're all pretty soft metals, and they are all very chemically reactive with water. Representative elements are those defined in groups 1 and 2 and groups 13 and 18. So these elements here, groups 1 and 2 and 13 to 18, are called the representative elements. Transition metals are called the D block metals, and they're located right here. Okay, and that's because their D blocks get filled up as we go across the periodic table. So let's do an electron configuration for iron, and then let's circle the valence electrons. So here is my periodic table right here. I've got it in front of the text over here. I find iron. Iron has 26 protons, so 26 for its atomic number. And then again, I'm just going to use the periodic table here to figure out iron's electron configuration. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d, because remember, we go from 4s to 3d. 3d, 1, 2, 3, 4, 5, 6, 3d, 6. Now this one's a little trickier because it says circle the valence electrons. We have to remember that valence electrons are the ones with the highest principal quantum number. So iron has 2 valence electrons right there. The lanthanides and actinides fill the f orbitals. So these are the lanthanides right here. These are the lanthanides. These are the actinides. And they fill up the f orbitals. You're not required to know the electron configurations of lanthanide actinide elements. However, you are required to know that those subshells get filled, and then so you therefore need to know the electron configurations of the elements that come after them. Okay, so I've given you an example here, which is polonium. Okay, and so we're going to write the condensed electron configuration for polonium. I'm going to pull up my my periodic table here. I see polonium is right here. The nearest preceding noble gas that has a completed electron configuration is xenon. So that makes things a little easier for me. I'm just going to write, for polonium, I'm just going to write xenon in square brackets. So that takes me all the way up to here, right? And so then I look, so xenon is here. Then I'm going to have to fill this right here. So this is 1, 2, 3, 4, 5, 6. So this is 6s2. So 6s2. Then I'm going to have to jump and fill up all the lanthanides right here. 4f14. Then I fill up the D block elements. 5d10. And then to get to polonium, I go 1, 2, 3, 4, 6, P4. The ion charges of many of the transition metals can now be explained using our theory of removing electrons from the highest principal quantum number. So let's take a look at zinc and its 2+ ion. So I'm going to write the condensed electron configuration for zinc. Again, let's pull up our periodic table here. Okay, so let's bring it up. We've got zinc is right here. So I do zinc, and it's got 30 protons. Okay, I look at my preceding noble gas, that's argon. Okay, and so then I'm going to say 4s2, and then 3d10. Okay, so that's for zinc. Now, for the zinc 2+ ion, remember, I remove electrons from the highest principal quantum number. So the reason why it forms a 2+ ion is because 2 electrons are removed from the 4s orbital. So then I just have argon and 3d10. Now what we're going to do is we're going to take a look at the electron configurations for lead and both of its 2+ and 4+ ions. So the first thing I'll do is I'll just take a look at lead right here, and I'm going to write its condensed electron configuration. So lead is 82. So this is the neutral atom of lead. I write xenon. And then I have to recall here that xenon, and then I jump to 6s2. And then right here, I have to fill the lanthanides. So the lanthanides are 4f14, 5d10, fills up here, and then I get to lead right here, so that is 6p2. Okay, so lead forms 2 ions. It forms a 2+ and a 4+ ion. So let's take a look at the valence electrons that are present here. There are 2 electrons in the 6p2, and there's 2 electrons in the 6s2. So if I want to form the lead 2+ ion, so I'm going to write lead, and I'm going to write 2+. Remember, these are my valence electrons right here. I'm going to remove them from the higher energy first. So I'll write xenon, 6s2, 4f14, 5d10. So that's for the 2+ ion. And then for the 4+ ion, I'm going to go ahead and remove another 2, again though from the highest principal quantum number. And so xenon, get rid of these ones, and I just write 4f14 and 5d10. There are other more sophisticated configurations that are not easily explained, but they require theories beyond the scope of this course and therefore not evaluated. Okay, so that right there covers using the periodic table to more easily come up with electron configurations, looking at the locations or knowing where the valence electrons are, and then removing valence electrons according to the highest principal quantum number.